It's my pleasure to introduce our speaker today. Robert Pappalardo is Senior Research Scientist at NASA's Jet Propulsion Lab. I think that this is, of all the federal labs, the one with the coolest name, evoking jetpacks and other science fiction dreams. Robert received a BA in Geological Sciences from Cornell and a PhD in Geology from Arizona State University. His research interests cover the geology of planets and their moons in our solar system and the possibility of life on them. And today, Dr. Pappalardo will be talking to us about Jupiter's moon, Europa.
Appreciate the big crowd. We're going to lower the lights a bit here because the slide setup is a little bit dark, but hopefully you'll be able to see what we're talking about. And what we're going to talk about today is some of the moons of the outer solar system and why they are such a high priority for exploration, and why we think that some of them, at least, could potentially be habitable environments, places where maybe we'd be able to find life. And we're not talking about whales, we're talking about single-celled organisms, potentially, because within these icy moons, they're mostly, or some of them are kind of half ice, half rock, but the outer portions are mostly ice. It could be warm enough down below their surfaces that there is liquid water. And water, of course, is a key ingredient for life. Necessary, but not sufficient. And I will concentrate on Europa, the one in the foreground here, and I'll have the same problem. This talk that I have in past talks, I get hung up on Europa and then I have to speed through the other satellites, but we'll do what we can. And that's Europa and a few of the others that we'll talk about. Ganymede, Enceladus, and Triton are there. So first we want to define a habitable environment. What do we really mean? What are we looking for? Life, as far as we know, needs 4 ingredients. A solvent. Water is a really good one, works on Earth. Maybe there could be other solvents too, as we'll see at Saturn's moon, Titan. Essential elements, the elements from which organic materials are built. Carbon, hydrogen, oxygen, phosphorus, nitrogen, sulfur, etc. Chemical energy, what do we mean by that? What we mean is what life lives on, essentially, is chemical reactions. And simple organisms in an ocean that might exist under the surface of Europa are not going to have access to light for their energy. But instead, there may be chemical disequilibrium that can supply the energy for metabolism. The more we explore extreme environments on Earth, the more we realize that organisms can live on reactions that don't involve photosynthesis, like get hydrogen and iron together, and they can they can undergo a reaction that liberates energy that life can use. And there are many such chemical disequilibria that could power life. So that's a tough one to explore, but that is key in understanding whether a place like Europa might be able to have life. Is there chemical disequilibrium in its ocean? And then the fourth one is stable environment, because life presumably needs time to develop. And if there is a nice, warm, cozy environment with elements and water and chemical disequilibrium, and it only lasts a few million years, is that sufficient? Or really, do you need it to last 1 billion years? Well, we don't know the answers to all these things, but we can look at the suite of satellites and see what the possibilities are. So we use Earth as our example. It's the one we know. It's the only place we know of life, and so it's the only example we have. And we want to kind of apply that to the whole array of large and middle-sized moons that are out there. Jupiter has 4 big moons, the Galilean satellites, named for Galileo, who first observed them. The Saturnian system has 1 big one, and the Neptune system has 1 big one. We're not counting Pluto anymore as a planet. It's a dwarf planet, but we might potentially think about it and its icy cousins as well. But the ones that are labeled here are the ones we'll concentrate on. Europa, Ganymede, and Callisto at Jupiter, Titan, and tiny Enceladus at Saturn, and then we'll briefly look at Triton at Neptune. When we talk about ice or ices, really we're talking about anything that's volatile in the Earth environment and condenses out as an ice in the cold outer solar system. Well, water ice is everywhere in the outer solar system, such that Ganymede and Callisto are half ice and half rock. There's also CO2 ice out there, which we know is dry ice. And as we go further out in the solar system, then ammonia, carbon monoxide, and methane exist out there and are expected to have condensed out of the solar nebula when the planets and their satellites formed 4.5 billion years ago. And then even nitrogen ice is observed out at Triton and Pluto. It's so cold that nitrogen exists as a solid on their surfaces. Oh, and I should mention, it's so dark, you can't even see it. Well, it's probably close to its real albedo. Earth's moon for scale. Europa is about the size of Earth's moon.
You said it's the Earth's moon up there?
Yeah, up in the corner. But it's a little hard to see. So let's start with Europa. I'll try to race through it so I can get to the others. It's a strange looking place. This is Europa stretched out into map projection. There it is if you were looking at it. Very few craters. Doesn't look like our moon. It's bright because this surface is mostly ice. And there's some darker reddish stuff as well. It's crisscrossed by ridges and bands and grooves that still remain a little mysterious, as we'll see, and this darker kind of mottled terrain. Very few craters. Here's one, Pwyll, or Pwch if you're Welsh, but there are very few others. So few that we can estimate the age of Europa's surface because we know about how often it should be hit by something big enough to make a big crater like Pwyll. And that surface age comes out to be about 60 million years old. So the whole thing is 4.5 billion years old, but something has repaved its surface in the last 60 million years, 1% of the age of the solar system, the time since dinosaurs roamed the Earth. That's just a blink of an eye geologically, even though it might seem a long time to us. This is what the ridged plains, the bright regions, look like close up, crisscrossed by these ridges and grooves, a bizarre surface. But again, mostly ice we're seeing here. It's cold enough that ice can exist over the age of the solar system on the surface. And this is what that more mottled, darker terrain looks like, a little like you took the ridged plains and cooked them on a grill or something. It looks a little like hamburger there. There's a little crater here. There are some little craters sprinkled around, mostly thrown out from bigger craters. So we can actually use the surface geology to tell us something about the interior. But first, the Galileo spacecraft that visited and took most of the pictures I'm showing, visited the Jupiter system. It flew, oh shoot, it's not repeating. Darn that thing. If I click on it, will it repeat? No. All right, let's talk about tidal flexing first. The Galileo spacecraft orbited Jupiter from 95 to 2003. It made many flybys of the satellites and about a dozen past Europa. And as it did, it could measure the gravity field of Europa somewhat, just by flying by it and tell us something about the density structure, how centrally condensed Europa is. And so we know it has an iron core, a rocky mantle, and then its H2O is concentrated in the outer 100 kilometers. So this is not to scale. What I was hoping would repeat, I was hoping my little movie would repeat so you could see Europa flexing. Come on, do it, do it. Try one more time here. Oh, there it goes. Okay, so as Europa orbits around Jupiter, it flexes in and out because it's an eccentric orbit. It's getting closer and farther from Jupiter as it orbits. And so as it gets a little closer, it gets stretched out a little more, and as it gets farther away, it contracts a bit. And this flexing in and out is generating heat. Like bending a paper clip back and forth, it generates heat and is what may allow liquid water to melt out as one goes down within Europa.
Is this always along the same axis, meaning that it rotates and turns around, or is this a different axis?
Like our moon, most moons in the solar system show the same face toward their parent planet as they orbit around, because they're tidally locked. But as we'll see in a minute, Europa might not be perfectly tidally locked, but it's essentially, over our lifetimes, tidally locked and showing the same face toward the parent planet. As it orbits, its tidal bulge is also nodding back and forth across the face of Europa because it's facing toward Jupiter, and that tidal bulge. And so that back and forth kind of sloshing of the tidal bulge is also generating some heat. So we don't know if, again, it's a little dark, but we don't know if some of that heat is concentrated in the rocky mantle, but that heat at least is concentrated in the icy shell. And where the ice is warmest is where more heat is generated. So if there really is enough heat to melt out water, then that warm ice at the bottom of that floating ice shell is where the heat will be concentrated. If there's no ocean in Europa, then this flexing would only be a meter, and there wouldn't be much heating at all. If there is an ocean in Europa, that flexing will be 30 meters. And we can measure that with a spacecraft, which is what we hope to do in sending an orbiter to Europa as the next big mission sent to the outer solar system. And we'll touch on that at the end. Something else the Galileo spacecraft was able to do was measure the magnetic field in the vicinity of Europa. You wouldn't expect Europa to have a magnetic field of its own, but unless it has a hot convecting core, that's not out of the question. But Europa is immersed in Jupiter's magnetic field, which is the most powerful magnetic field in the solar system. So Jupiter is behaving as a big magnet, and Europa is orbiting around within this enormous magnetic field. What the Galileo spacecraft measured as it flew by Europa is that there is a magnetic field there, and its polarity seemed to change depending on where Europa was relative to Jupiter's magnetic field, whether it was above or below the plane of Jupiter's magnetic equator. Not that Europa is moving up and down, but the magnetic field of Jupiter is tilted by 10 degrees. So as Jupiter orbits around, its magnetic field is sort of flopping around, and Europa is sometimes above and sometimes below the magnetic equator. And so Europa seemed to be having a magnetic field to counter Jupiter's magnetic field. And if any of you are taking E&M class or remember your old electricity magnetism class, you realize that a conductor moving through a magnetic field will generate its own magnetic field. And that's what Europa seems to be doing. It seems that Europa is behaving as a conductor as it moves through Jupiter's magnetic field. And that conductor seems to be very shallow below its surface. Something like 30 kilometers or less below its surface is where this field is being generated. So what could be a conductor within Europa 30 kilometers down? Well, that's about the depth that an ocean should be if it exists within Europa. So it seems that a salty ocean is making Europa conductive and making the magnetic field signature that we see. That's actually the best evidence for an ocean within Europa today. There's theoretical evidence from the tidal heating that says, oh, probably it should melt out, but this is the best direct measurement. And we'll look at some of the geological evidence that there's an ocean as well. From an orbiting spacecraft, by the way, we can get at the salinity and thickness of that ocean, which will be very exciting to do from orbit, measured for a long time at Europa. We'll know how saline and how thick that ocean is. We think something like 80 kilometers thick, but we don't know how salty. So this gets at the question that you'd asked earlier. Europa mostly faces toward Jupiter as it orbits around. Oh, and I should say it goes around every 3.5 days around Jupiter. It's just whipping around as it flexes in and out by probably about 30 meters. But if there's an ocean down there, and this is a little more to scale than previous slides, if there's an ocean down there under the ice, then actually that icy shell should slowly slip, or could slowly slip, relative to the interior of Europa. What keeps a satellite facing toward its parent planet is that there are concentrations in mass that get locked in toward the parent planet. Well, a floating ice shell isn't expected to have a concentration of mass, so it could actually slip relative to the interior. And the theory says it would slip around once in something like 10 or 100 million years, very slowly slipping around the surface. And that all seemed like theory until people realized if you map out Europa's global scale lineaments, those lines on the surface, and you assume they form from pulling apart of the surface, then you can compare them to the stresses, red and blue here, that are predicted from this slow slipping of the ice shell. So as the ice shell slips, it changes in shape as it moves over Europa's distorted surface. And these arcs, the features on the surface, are kind of perpendicular to the direction that the surface is being pulled, the tensile direction. So that says this really might be going on because this global pattern of lineaments fits the predictions of this slow slipping. So indirect evidence for an ocean down there within Europa from the global geology. Now you might wonder about another stress, that is the stresses from this flexing of Europa as it orbits around in 3.5 days rather than 100 million years. This arrow is showing the magnitude and direction of tensile stress in southern latitudes on Europa as it changes. Oh, none of my movies are looping. As it changes as Europa orbits Jupiter. So each arc, you'll see if I can play the movie again, is one orbit around Jupiter where the stress direction is rotating and changing in magnitude as Europa flexes in and out and nods back and forth. And if it's assumed that a fracture forms and propagates across the surface at about the speed a person can walk, then that's what this movie's showing. Let's see if I can make it at least play again. So that's demonstrating the changing direction and magnitude of stress, plus adding in a speed of about 2 kilometers per hour across the surface. It would trace out these arcs. Well, that's a wonderful model for explaining something that was a 20-year mystery from the time Voyager flew past the Jupiter system in 1979 and first viewed Europa from afar. There were these strange patterns seen on the surface. We didn't know what the heck they were. There were all kinds of strange explanations. And 20 years later, a couple of smart folks at the University of Arizona realized that this changing, rotating stress, if a fracture propagated across the surface, could trace out an arc. And they very well match what we see. Again, why do we care? What does that have to do with water and habitability? Well, because these are potentially explained by this stressing, this flexing of Europa, like I said, if there's no ocean, that flexing is negligible. If there is an ocean, that flexing is a lot. So these cycloidal fractures tell us that there's probably an ocean down there at the time they formed, simply because they exist and they fit this pattern from the tidal stressing. An ocean is necessary for the tidal amplitude, the amount of tidal stress that would be needed to break the surface and make these cycloidal fractures. So let's see. Again, it's a little dark. I apologize for that. But we're going to zoom in and take a look at one of Europa's ridges close up here. These ridges seem to travel across the surface in pairs. It's one ridge on each side and a valley down the center. And they cut across the older plains. This thing's about 2 kilometers across, a little more than a mile across. It's probably a couple of 100 meters high. They're the most common feature on Europa, and we don't know how they form. We have some ideas. The idea I like the best is that there was a fracture that cut through. There are fractures that cut through the cold, icy surface, and then something happens along those fractures to form the ridges. Now, what that something is debated. Some people argue that water spews out from the ocean, or the squeezing back and forth allows water to pump out, or warm ice is rising up from the interior, or there's compression going on, or dike-like cracks below the surface. But the model I like is that the surface, the cold ice, is cracked by this tidal squeezing. And once it's cracked, either side of the fracture is going to move back and forth over the course of the Europan day. Because those stresses are rotating around. What happens is if you have a crack, then each side of that fracture is moving back and forth. So kind of like the San Andreas fault is slipping, but instead of always slipping one way, it's going back and forth over the course of a Europan day, over the course of a Europan orbit of 3.5 Earth days. So that moving back and forth is going to generate heat, just like rubbing your hands together generates heat. And that warm ice will tend to rise up a little bit, and it might even be a plane of weakness along which there can be some compression. So so that means these ridges themselves are a consequence of the tidal stressing, of the fact that there's an ocean down there and Europa's ice shell is moving up and down and back and forth, breaking and sliding as it does. So lots of indirect evidence for an ocean from the geology. There's some more cool evidence for an ocean that is also relevant to the habitability issue for Europa. There are these, my movies are stopping. There are these pits and spots and domes sprinkled about Europa's surface. And here are a couple up close. The light's coming from the right. This kind of is football shaped with a crack along the crest. And this is another like spot of hamburger or something on the surface, broken up terrain. Well, what can probably form things like this are what are called diapirs, blobs of warm ice, like wax in a lava lamp, that have risen up through the ice shell to the surface. So what we think is going on is that warm ice from the base of the ice shell is moving upward, and colder ice is sinking downward, and that warm ice is getting out of the shell, emerging at the surface. So that's important if you want to know whether, if there is life down here, whether we could detect it at the surface. These blobs of warm ice may be dredging deep stuff up to the surface of Europa. Let me see if I can make that movie work, which is a simulation of this process of convection that we think might be happening in Europa's icy shell, with this being the ocean ice interface and warm stuff. Whoops, it's a little hard to see. I apologize. Warm stuff rising up from the base and toward the surface. It's a little tough to see in that animation. It's a little dark. And the near surface, though, is very cold. It's actually pretty tough for these ice blobs to get out, and that's a problem we're still working on. It may be that they're chemically buoyant as well, because maybe they're clean and the rest of the ice shell is somewhat salty. So it's not just important as to whether stuff can be dredged up from the ocean to the surface if you want to detect life or byproducts of life, but also whether stuff from the surface can get into the ocean. So why don't we return to that issue in a minute? Because if stuff can get from the surface to the ocean, that's going to be really good for potential habitability. We'll come back to that in a second. There are bigger blobs of this chaotic modeled terrain. Here's an image of some of them where these blocks have broken apart, moved around on the surface, jostled each other, and it's aptly called chaos terrain. And we're trying to understand how it forms. One idea is that the ice shell literally melts and liquid water was exposed at the surface. It's actually very hard to do. You need a lot of heat to melt a several kilometer thick sheet of ice. And only if it's less than 6 kilometers is it even possible, because otherwise the warm ice will just flow in to try to fill the hole. And we think the ice shell is probably thicker than that. But maybe it's these blobs of warm ice coming up and breaking apart the ice shell, especially if that ice shell is somewhat salty and can melt out in places. Let's see if this is going to be too dark to show. Let's try it. It might be too dark. We're zooming into one of those chaos areas, and right now it looks pretty black, doesn't it? Let's see. Let's see when it goes to the next zoom level, whether it will be more visible. Let's see. Okay, here we go. There we go. Now you can see the blocks. That works. Thank you. But now they can't film me. That's about the size, that's about 5 kilometers across, the size of a small city. And those two halves of that block have yanked apart and moved around. And now we're going into some of the Galileo spacecraft's highest resolution pictures, 10 meters per pixel. You can count the number of such pictures on your hands and toes, unfortunately. But you're zooming in so far that you can start to imagine that's like Monument Valley out in Arizona or Utah or something, with a steep cliff and then a shallower face where debris has fallen down. And when we go out into this hamburgery terrain, this model terrain, it doesn't look smooth like a skating pond, like there's been water there, but more like these ice blocks, there's one, have crumbled in place. There's an old ridge, not looking too happy. This iceberg is kind of a kilometer across. The Titanic would be about that size in comparison. Back across one of those ice blocks. So I don't think this was literally liquid water. I think it was probably more likely a slurry, a slush, where warm ice came up from below and partially melted out the surface. Though that's really still a big challenge when your equilibrium surface temperature is 100 degrees Kelvin. What's that, minus 300 and some odd Fahrenheit. Okay, so I don't know if you want to put the lights back so people don't snore. So this is a summary of what Europa's icy shell geology might be like. I didn't talk about these bands, which are areas where we think the icy shell has pulled apart along warm ridges that are, if there are geologists in the crowd, that might be like mid-ocean ridges that have yanked apart. But we think the ice shell is probably about 20 kilometers thick based on the magnetic signature, based on impact craters. There are a couple that have appeared to have pierced through the ice shell and suggest that it's about 20 kilometers thick. This process of convection should kick in when the ice shell is about 20 kilometers thick. So there are a lot of indirect indications that that's probably the right number. Right, so I said I'd talk about the importance of getting stuff from the surface to the bottom. At the surface of Europa is exposed to this radiation environment from Jupiter. Remember, immersed in Jupiter's magnetic field. Well, trapped in that magnetic field are very high energy particles, protons, electrons, ions, that are slamming into the ice. And that knocks particles off of Europa and creates a very, very tenuous atmosphere. In fact, it could knock particles off to the height of a spacecraft if a spacecraft's at 100 or 200 kilometers altitude, where we could measure the composition of those particles, and that's something we plan to do with a future orbiter. Well, they also change the chemistry of the surface. So they hit H2O and break it apart, and the H floats away, and the O stays behind. So there's actually oxygen trapped in Europa's ice. In fact, we think it might be trapped in little bubbles. Hydrogen peroxide forms on the surface. So oxidants form, things that are oxidizing form on the surface. Those are great fuels for life if they could get into the ocean. They would be great for metabolism. So it's important to understand whether the surface stuff can circulate into the ice shell and down into the ocean. So the more we understand how these ridges and form and how this convection works, the better we'll understand whether it's possible to get oxidants down there. What we really want is kind of an X-ray of the ice shell to tell us what are those processes. Where is there liquid water? Is there liquid water within the ice shell? Is it draining downward? Well, we hope to get an X-ray of the ice shell with an orbiting mission that will use radar that can penetrate through ice. Radar, 6 meters in wavelength, can penetrate right through ice, bounce off water, and back to the spacecraft. And this is done in Antarctica. It's been done at the polar caps of Mars, and we hope to do it at Europa with a spacecraft in the future. So to summarize Europa in terms of potential habitability, water, we think so. We're pretty sure there's a global ocean there, warm, relatively warm, salty water ocean that could potentially support life. In terms of the elements, I didn't talk too much about the chemistry, but when Europa accreted, it may have had lots of CO2. Carbon is an important thing to get there if we want life. Impactors, later impactors, bring carbon. But it's important to note that radiation destroys organics in the upper tens of centimeters of Europa's surface. So the hard part is, even if we don't observe them, it doesn't mean they're not there. We hope to, with a future orbiter, find maybe small patches where there's been recent communication with the subsurface and maybe radiation hasn't destroyed the organics yet, if there are organics, so that we can get at whether there really is organic stuff in the subsurface that's being exposed. Now, I mentioned oxidants and the importance of getting them into the ocean. So that gets to the next issue of chemical energy. Radiation creates them at the surface. What about the reductants? What about the other half of the necessary chemical reaction? If the mantle of Europa is hot, then like on the Earth's ocean floors, there can be reactions between water and hot rock that generate all kinds of great reductants that could be pouring out of the ocean floor of Europa. For that matter, just serpentinization itself, the process of olivine transforming into serpentine, generates reductants. So really the limiting factor is probably the oxidants, not so much the reductants. So this surface circulation is still the important factor, we think. And then this issue of stable environment. Well, as a large satellite, Europa retains its heat more easily than a small satellite. It's probably been in this tidal resonance and being tidally flexed for a long time, billions of years, maybe since the beginning of the solar system. An interesting factor is, though, that the activity level might not be constant. It might vary with time. There are some models, that predict that it may vary over 100 million year timescales as tied to the orbit of Io, strangely, because Io is pulling and pushing on Europa. So it's interesting to think that Europa might go through 100 million year cycles of more and less activity, and if there were life down there, could it survive through the more dormant stages? So it might be a little bit of an issue, but less so than a small satellite, which has a lot more trouble retaining its heat. Okay, not bad. I still have 20 minutes to rush through the rest of the solar system here. Ganymede, biggest moon in the solar system, the size of the planet Mercury. It has an intrinsic magnetic field. So I talked about an induced magnetic field indicating a salty layer within Europa. Ganymede has an intrinsic magnetic field, its own magnetic field, because it has a warm convecting core. So we know that because the Galileo spacecraft measured the signature of a magnetic of an intrinsic magnetic field, one that's not varying in response to where Ganymede is relative to Jupiter's magnetic field. So Ganymede's hot down there. That's actually part of the story about Europa's activity. Something made Ganymede hot down there. Must have happened in the last billion years. So that's tied into this whole issue of the orbital evolution of Europa and Io as well. Maybe there was some big tidal event that kicked up the eccentricity of Ganymede's orbit, something like 1 billion years ago. So by learning about the interior of Ganymede, we actually can say something about the history of the system and the history of Europa as well. But back to the ocean, I digress. Ganymede has so much H2O within it, such a thick water ice layer, that its ocean is probably trapped between ice above and higher density forms of ice below. So ice isn't just ice one like in our freezers. That's true at Earth pressures. But at the much larger pressures within a big satellite like Ganymede, there can be other forms of ice, ice 2 and ice 5 and ice 6. And for Vonnegut fans, there is an ice 9, but it doesn't exist within Ganymede. That would be bad. So there are forms of ice that sink, these other forms of ice sink relative to water. And where the ocean should occur is at about 150 kilometers deep within Ganymede, because it has so much H2O that's the location of the pressure where ice melts at the lowest temperature that it can melt. So Ganymede's ocean is probably much deeper than Europa's. And there's indirect evidence that matches that, like big multi-ring structures on Ganymede that may have penetrated to its ocean from big impacts 4 billion years ago, and they suggest that they've penetrated down about 100 kilometers. Ganymede has interesting geology that suggests rifting and yanking apart of the surface. So potentially an active interior, but longer ago its surface is cratered. So it's probably not active at its surface today, even though down below it seems to be warm and convecting. Oh, I said 150 and this says 170, but I think 170 is probably where the ocean is centered. That's probably right. So let's see. Then there's also Callisto. Similarly, whoa, again, a little dark, sorry. The rest of Callisto here is a very dark moon. It's probably what it would look like if you tried to see it. This is what the surface looks like from Galileo. It's a cruddy-looking surface. Callisto has kind of been rotting in place. What's going on here is these craters look kind of sad because Callisto's probably not been very active geologically, but its surface contains CO2 ice, which is slowly evaporating to space and dropping its dark dirt behind to cover up the rest of the craters. So there's not much happening geologically there. But even so, the Galileo magnetometer says it's showing an induced magnetic field signature. Oh, I neglected to mention at Ganymede, even though it has this intrinsic magnetic field, the Galileo magnetometer eked out the signal of an induced magnetic field as well, suggesting, helping to confirm an ocean within Ganymede. At Callisto, the signal is very clear for this induced magnetic field, that there's an ocean in there, even though it's geologically dead. It's not a very warm body. It still seems to have enough heating to have an ocean in there. It's probably because there's some salts or maybe even ammonia that serves as antifreeze and lowers the melting temperature of the ice to the point where an ocean can exist. But again, sandwiched between ice above and ice below, a perched ocean, if you like. So for Ganymede and Callisto, let me scan back to Ganymede here for comparison. An ocean that is not in contact with rock and which is buried 150-ish kilometers below ice is not going to be nearly as attractive for habitability as Europa, because it's not going to be able to get the chemical ingredients that could get into an ocean from contact with a mantle. It's not going to be able to get its reductants. It's not going to be able to get its oxidants through 150 kilometers of ice. And we think it's probably geologically dead at the surface compared to Europa, which seems to be pretty active today. So we're talking surface age at Ganymede of something like 2 billion years. And the same goes for Callisto, but even more so because it has no geology, no active geology mixing surface material into the interior today. So not as attractive places to go looking for life. Now, let's move out to the Saturn system. Titan. Titan's an amazing place. The Cassini spacecraft is right now at Saturn, orbiting Saturn, making flybys of Titan. Its mission's recently extended for another 7 years, so it's going to make 50 some odd more flybys. This dark slide is a prediction of what might be found on Titan. Well, the key things are listed here. Before Cassini, and amazingly, about all of them have been shown to be true. And that doesn't happen too much in science. So Titan has a smoggy atmosphere, an atmosphere of nitrogen and methane. So like our atmosphere, the key ingredient is nitrogen, the most dominant ingredient. And then there's the also-ran ingredient, and that for Titan is methane. Well, take nitrogen and methane and allow it to sit there with ultraviolet radiation from the sun hitting it, and it breaks the nitrogen and methane apart. And from nitrogen and methane, you can make all kinds of interesting organics if you mix and match the C's, N's, and H's. So, in fact, it was predicted, and it seems to be true, that it's making ethane and acetylene and all kinds of complex organics, some of which are predicted to precipitate down onto the surface as solids or even as liquids. A big issue is that the methane breaks apart and the hydrogen escapes, and so you need to resupply the methane somehow on Titan, or you're going to lose the atmosphere over time. Recent thought is actually maybe Titan is losing its atmosphere over time, but there may be some resupply as well, and that's a topic of current debate. But methane-ethane rain is predicted, which might make lakes or seas or even groundwater, ground fluids, ground hydrocarbons at Titan. And we have our rotating globe. The Cassini spacecraft, so if you looked at Titan, you see its smoggy atmosphere. You can't see down to the surface. But the Cassini spacecraft has an infrared capability, and infrared at specific wavelengths can see right through that atmosphere and down to the surface, which is what this map is made from. And Cassini also has a radar, not a radar with 6-meter wavelength that will go right through the ice like we're talking about for Europa, but radar with 2-centimeter wavelength that bounces off the surface and back to the spacecraft. So it can use that radar to map the surface. And this is an example of radar images, radar signal bounce off the surface of Titan back to the Cassini spacecraft in its north polar regions. And I wonder, maybe we can kill the lights again just for this one, because that top one's not showing up. Thank you. There we go. That shows up better. And this is what we see in the north polar regions of Titan. Every indication is that these are lakes on the surface of Titan. And with the infrared instrument, it's been confirmed, the detection of ethane has been confirmed in those lakes. There have even been some changes observed over the course of the 6 years that Cassini has so far been at Saturn and flying by Titan, where some lakes have appeared in the south that weren't there before, and some lakes seem to be drying up and changing their shape. Okay, we can flip those back on. Thank you. So it seems that Titan really has liquids on its surface. It's like the stuff of science fiction. Someday we'll send a spacecraft to go sample those lakes. At Titan, you could send a balloon or a plane even to explore because of its atmosphere. This is an image taken by a probe that Cassini released that did go down to the surface of Titan. And you can see very characteristic patterns suggesting drainage, that there has been rain. And there's evidence for clouds appearing and disappearing, clouds appearing and then little dark spots suggesting lakes on the surface. So it really seems to have an active weather system. And that probe actually survived. The Europeans built the Huygens probe, survived onto the surface of Titan. And this is an image of the surface from the Huygens probe. These ice blocks are about 6 inches or so across next to the spacecraft there. So Titan is an interesting place to think about in thinking about the existence of life in our solar system and beyond. We're used to thinking of water as the necessary solvent. What about ethane and methane? Can that work for supporting life? Could there be temporary water ponds made by impacts? If you have organic molecules sitting around for a few billion years, or maybe even just hundreds of millions of years, is there a natural selection of organic molecules? Or are we going to be able to get at the origins of life by looking at the organic soups on Titan's surface? Could it support some sort of weird life that uses ethane and methane as a solvent? And one idea purported recently is hydrogen and acetylene may be able to provide the chemical disequilibrium that life would need for metabolism. Then you have to think about whether that's going to work at 94 degrees Kelvin, which is the surface temperature across Titan. Not out of the question and worth thinking about. But if you want to search for water, Titan has that too, way down below its surface. Just like Ganymede and Callisto, it probably has an ocean 150 or so kilometers down. Actually, Titan, well, no, let me stick with that. That's probably the right answer. It's been argued that maybe that ocean is shallower, as shallow as 50 kilometers. But that ocean probably has ammonia in it. Remember, as we go out in the solar system, we get more volatile ices, more volatile materials. There's going to be more ammonia out of the Saturn system when it formed. And ammonia, for those who know how to read phase diagrams, here it is for fun, but temperature versus percentage ammonia. And this indicates that, well, with pure ice, no ammonia, it melts at 273, right? That's 0 degrees Celsius. Pure ice does. But add ammonia, if you add 30% ammonia, then it melts out at 173, 100 degrees Celsius less. So ammonia is a great antifreeze, is the point. And so just a little bit of ammonia will allow an ocean to melt out relatively easily out there in the Saturn system and beyond. But ammonia is known to be deadly to Earth microbes. So maybe an ammonia-water ocean is not a great place to be after all. Oh, this is the slide I was looking for before. I forgot I moved it to after Titan. But so for all three, Ganymede, Callisto, and Titan, these deep oceans imply little ocean surface communication. These perched oceans between ice layers imply limited chemical energy from below. They're high pressure, low temperature, maybe salt or even ammonia rich, and so not as attractive for life, which is why, again, Europa kind of rises to the top of places to go explore. What about smaller satellites? And out there in the outer solar system, or even Pluto, whoops, the dark stuff is showing the rocky portion of these satellites, that there might be ammonia-water oceans within even smaller satellites. Triton at Neptune. Oh, here's Pluto. So it too could potentially have an ammonia-water ocean within. These are not supported by tidal heating. This is just from radioactive decay. Because if you add ammonia, the ocean can melt out much easier. So even just the heat from radioactive decay of the amount of rock we think is within these moons and dwarf planets, in the case of a few of these, that could be enough to make an ammonia-water ocean within these bodies. There could be some serpentinization or hydrothermal activity, at least early on in the history of these objects. So it's not impossible to think about life even within these middle-sized objects. But again, ammonia-water ocean may not be a great place for life, and there's certainly less chemical energy and heat than in a place like Europa. Just a quick look at Triton, moon of Neptune, not to be confused with Titan, moon of Saturn that we looked at. Triton is a bizarre surface. They call this the cantaloupe terrain, maybe for obvious reasons. There are these dark streaks that are thought to be emanating from geysers. It might be that liquid nitrogen exists just below the surface of Triton and is spraying out in places. There are areas that look like there's icy volcanism, ice volcanoes. There are areas that look like they may indicate convection, that cantaloupe terrain of the ice shell, and then close-ups of these dark streaks that may be the heads of geysers with dark material strewn out. And oh, this is a little too dark to see that there's a streak that seems to stick up above the surface. There's a very tenuous atmosphere of Triton. These things seem to blow down wind. So Triton may even be still active today, this moon of Neptune. And I haven't seen anyone try to model what its ocean might be made of, considering there's methane and nitrogen and CO2 and CO and H2O all mixed into its ice. But let me skip that one and go right to Enceladus, because we're running out of time here. Oh, and my movie's not going to show, is it? The Cassini spacecraft, back at Saturn now, this is a tiny moon. This moon is as big across as the state of Arizona is across, about 500 kilometers across. The Cassini spacecraft noticed something really weird happening down at the south pole of Enceladus. And let me see if it's going to run my movie. Maybe not. That's okay. There are active jets streaming off, jets of H2O streaming off from the south pole of Enceladus. Something's going on, spewing water vapor out into space at Enceladus. And when you look at the surface and trace where those plumes are coming from, they're coming right from these big scars on the surface of Enceladus. They're somewhat bluish in this false color image. They're often called the tiger stripes of Enceladus. The whole south pole of Enceladus is showing evidence for lots of geologic activity, no craters, they've been wiped out, or very few, and active jetting. And here's what one of those tiger stripe features looks like close up. It sure looks like one of those ridges at Europa. Maybe Europa used to be real active and it isn't today, or maybe Europa will be active like Enceladus is again soon. So maybe it's the same kind of thing, rubbing back and forth of fractures, which is causing this jetting somehow. So what do we know about Enceladus? Well, I mentioned it's active down there at the South Pole. It's so active that we can actually measure the heat coming off the surface of Enceladus using the instruments aboard the Cassini spacecraft. And the heat is concentrated along those fractures as well. Heat meaning these get up to something like 140 Kelvin, and the background temperature is about 60 Kelvin. That's pretty darn warm for the south pole of an icy moon. We can measure the contents of those plumes, and there's nitrogen, CO2, CH4, and some simple organics. Acetylene and benzene are pouring out of Enceladus. So Enceladus really does have some organics down there. Tidal heating is presumably the power source here. There is active debate over whether this activity implies an ocean, or a sea really, down below the south pole of Enceladus. It's such a small moon that it should cool off very quickly. So it's surprising that Enceladus would show any evidence of activity today. But there it is, and now we have to explain it. But the great amount of heat pumping out of Enceladus suggests it just can't be in a steady state, and that it's going through a burst of activity, and that we're seeing it at a very unusual time. That maybe every 100 million, maybe its active cycle lasts 10 million years or so, or 100 million years, and that's only happened 3 or 4 times through the whole history of the solar system, and we're catching it now. Let me skip that in the interest of time. So, ingredients for life. Does Enceladus have them? Well, liquid water. Here it says probably an ocean at depth. Again, I think there's somewhat of a debate, but without an ocean, there couldn't be much tidal heating. An ocean actually enables tidal heating. It's a little bit of a chicken and egg problem, but it's thought there is probably at least a sea down at depth within Enceladus under the South Pole. Possibly it's connected to the surface through fractures that are venting out to form the jets that we see. Does it have the right elements for life? Well, simple organics are observed in that plume, which is just astounding. Does it have chemical energy? It's not really clear. The models of the ocean chemistry and surface interior exchange are kind of immature for Enceladus. It's not clear if stuff from the surface is getting into the ocean or not, and whether there is a distinct rocky core down there. And again, that activity may be transient. I think the biggest problem for potential life at Enceladus is that the activity might just last 10 or 100 million years and then die out. Is that enough time for life to get going inside a moon? Well, to summarize, because I realize we're about out of time, there may be as many as 13 oceans in our solar system. So that movie didn't know, it was so aptly named. Europa's, I would argue, is the best place to search for life and tell us about habitability because of its warm, salty ocean that is probably in contact with a rocky mantle below. Ganymede and Callisto have these perched oceans, not as attractive for life. The same goes for Titan's internal ammonia-water rich ocean, and then the fact that there's ammonia might not be so great for life at Titan. Titan also has these surface seas of methane and ethane, which are an interesting place to think about whether life could plausibly exist in such a solvent. Then there are the whole range of middle-sized icy moons and these Kuiper belt objects like Pluto, those kind of like icy asteroids, that might have oceans within, but again, potentially ammonia-rich. And then there's tiny Enceladus, so here you can see the size compared to the other. That's supposed to be a little wedge. And its bizarre activity related to tidal heating. So, I put together this very subjective scorecard. A lot of what you've heard is very qualitative and subjective, of course, with regard to liquid water, elements, chemical energy, and stability. And one can, it's kind of fun to argue about the potential ratings here, but I'd argue Europa scores very highly in all, where blue is even better than green in the stoplight chart, whereas the others might have some issues lacking with regard to ammonia-water oceans or being small and losing heat, But it is interesting, especially to think about, again, about Titan, where'd Titan go, and its surface lakes. And I think Enceladus scores pretty high here as well as a potential place to explore astrobiologically, a place to explore whether life might actually exist there. And I alluded a few times to future exploration of Europa, and we're actively planning the Jupiter-Europa orbiter, which is planned to launch in 2020, get to the Jupiter system in late 2025, and then orbit Europa and do many of the experiments that I mentioned starting in 2028. So stay tuned. Thank you very much.
What about Mars and our moon?
Let's start with Mars. Mars may have water down below its surface in pore spaces. It's not going to have a global ocean, but it might have a hydrology system. There is certainly an active program to understand whether Mars is a habitable environment today. We know now from spacecraft evidence that Mars probably was a habitable environment in the past. So I think Mars is an attractive place to think about for whether life ever did evolve. And in fact, impacts should have blasted life off of Earth early on and over to Mars, and vice versa. In fact, it's plausible that life started on Mars and then was blasted from an impact over to Earth. And if life arose on one, it may have arisen on the other. But Mars probably has died out. So it's very interesting to think about whether there could be some fossil evidence on Mars for life. But it's less attractive place for current day evidence. But that said, for current day life, that said, there is a mission in the planning stages to look for trace amounts of methane in the Mars atmosphere. There have been some hints from Earth there may be methane in the atmosphere. It shouldn't be there. It's not in equilibrium. If it is there, maybe it's made from volcanism. Maybe it could be made from organisms down below the surface that are producing methane. So it is an active area of research. And so arguably Mars and Europa are the places to go. In terms of the moon, there's only trace water there. It's not the kind of place to go look for moon life. However, early in the history of the Earth, when life was getting going, there were still big impacts happening. And someday we're going to know how life arose on Earth because we're going to find evidence for it on the moon. There is certainly buried in the upper layers of the moon evidence of the first life on Earth that was blasted up there. And someday we'll sift through lots of that stuff and find evidence for it.
I never heard that life might have been blasted from Mars to Earth. Is that like a common theory?
Yeah. I'm trying to think when that arose, because it is relatively new. I think it was the late 80s where the idea came up, mid-late 80s. But then we found lots of meteorites. Oh, that was it, yeah. The reason people went back to the drawing board to think about that is there were lots of meteorites found in Antarctica, let me back up again. There's a class of meteorites where first we didn't know where the heck they came from. And then there were a couple found in Antarctica with gas bubbles that exactly match the composition of the Mars atmosphere. So we know that we have Mars meteorites in our collections now. So we have samples of Mars. But people couldn't figure out how they got blasted off. So they went back to the drawing boards and realized that you can blast material off relatively unshocked from the Mars surface to transfer to the Earth. It's a little harder to do that from Earth to Mars. You need big impacts, higher gravity. But early on, you did have big impacts. So yeah, since then, let's see, the late 80s, early 90s, People have been looking into that, and it's pretty well established that material can be transferred between the planets. But Europa, if life formed there, it's an independent origin. You're not getting stuff blasted off the Earth to get to Europa. Very little can get there, and it would hit at such a high velocity that it would vaporize. So if we find life at Europa, it had an independent origin.
Are there other possible reasons there could be an induced magnetic field in these planets other than the presence of a ocean?
The only other way you could make an induced magnetic field would be some other conductor in there. Well, actually, no. There are two things. There are two possible explanations. So one could imagine maybe the metallic core is the conductive stuff, but from the signal, the folks who've been working this have constrained how deep that's coming from, and they tell me, and I believe them, that it can't be coming from so deep. That looking at the signal, it must be coming from shallow layers. So I can't answer better than saying I have faith in them, but we can go down to their papers and try to trace where that comes from. The other thing is there are ionospheres, there are charged particles in the vicinity of these satellites that could conduct. But it's thought that these layers are so thin that they're not conductive enough to explain the result. So again, theorists are shown to be wrong, like in the thinking that we couldn't possibly blast stuff off Mars unshocked. And then, people figured out, oh, well, maybe we can do it. So it's not impossible that maybe we'll come along and say, oh, it was the ionosphere after all. But it's pretty confident that this is coming from conductors below the surface, shallow depths below the surface.
Well, thank you very much for coming.
Thank you.